Hello everyone, it's me again. I'm going to present the paper, Quantum Game Analysis of Privacy-Leakage for Application Ecosystems. And here is the outline. Firstly, I will give an introduction on background, and then the problem formulation, solution, and some special cases, and numerical analysis, and finally the conclusion. Okay, first let's come to the background. It is a common fact that most of these applications need to access some kinds of user-related information so as to provide their intended functionalities. For example, GeoNote. It is a context-aware application which call attention to the user once he or she is at a particular location. However, personalized applications often provide their functionalities by extracting sensitive data from users. Such a manner brings potential threats to users' privacy because some malicious applications may sell users' sensitive data to third parties for economic interests. Moreover, it is a common case that the user isn't able to control how the application deals with the user's private information. So the main challenge of this problem is that how to find a trade-off between service quality and privacy protection. Current mainstream solutions can be divided into two categories. The first one includes analytical tools or systems aimed to detect and analyze malicious applications with the aim of eliminating sources of privacy leakage. And the second one refers to privacy control measures for different scenarios, which normalize sensitive data or identities and selects a suitable probability of releasing data for users. However, these existing solutions typically address the privacy preservation problem purely from a technical perspective. Okay, now we come to the formulation. The aim of this paper is to provide a theoretical basis for designing effective and efficient privacy preservation solutions. The authors propose a concept of an application ecosystem that includes three elements: the user, application, and the adversary. Here, the trust impacts the reputation of the application, while the concealment from the adversary on the application influences the reputation of the adversary. And the reputation influential powers of the application and the adversary form two tensor forces in the application ecosystems, like its light side and the dark side. How does the power of the two sides impact the behaviors of three entities in the application ecosystem? In this paper, the main aim of the authors is to answer this question. Now let's come to the solution. There are three parts, including utility, construction, quantum model for the application ecosystem, and solutions for optimal strategies. Firstly, the utility of a player is affected by the subtle connections among the user, the application, and the adversary. Since the demands of user, applications, and adversaries are different, there exists a trade-off among them. Here is a framework of quantum model. Quantum model for application ecosystem is consist of the following three parts. Part 1. Integrating the tensor product of each player's initial state. And part 2 is to make each player capable of controlling its quantum bit according to some strategies. And the third part is to evaluate the payoff of each player according to the state of each player. Someone may ask why quantum game. There are three reasons. Firstly, the superior power of quantum game mainly stems from the extended strategy space and the concept of entanglement. Secondly, the game has its extended strategy space, Hilbert space, where the optimal strategy can be searched from a wider range. And thirdly, the idea of entanglement is to offer another perspective to depict the inner tensor forces among rational individuals. Here, the three parameters QU, QP, and QD dealt with a quantum model can be calculated like this. All that a player can control its strategy parameters, namely GU, GP, and GD. To get the optimal strategy for each player, the optimal strategy parameters, this way should be determined by maximizing UU, UP, and UD with the constraints of QU, QP, QD is no greater than 1 and no less than 0. This is a multi-objective and multi-constraint problem, and the authors adopt a multi-objective evolutionary algorithm to research for the Pareto optimal solutions. Here are some special cases. The malicious application would expose itself in any condition. And the best strategy of the adversary is QD equals to 1. That is not concealing the identity of the application. And the strategies of the user and the application, QU and QP, can be calculated like this. The malicious application is hardly detected, and the best strategy of adversary, this has been said in the last slide, and I don't know why the author presented it here again. It is the same like the last slide. The best strategy is QB equals to 1, and that is not concealing the identity of the application. And the best strategy of applications QP equals to 1, that is leaking privacy. The best strategy of the application depends on its expected utility. QU equals to 1 if Q is larger than K SD, and otherwise Q equals to 0. Okay, now let's come to the numerical analysis. These three figures show how the strategy of three players change with the repetition influential power of the application. One common trend among them is with the increase of parameter theta, QP goes down and QU rises up while fluctuation happens on QD. And these three figures show three players behave under different repetition influential powers of the adversary. And there is also a common trait, that is, the increase of parameter theta will result in declining QD and QU, but ascending QP. Here, figure 5 shows how the strategies of the user and the application change with the repetition influential power of the application. And the common trait of them is twofold. The first one is with the parameter theta increase, Q rises up while QP goes down. And the second one is the optimal strategies of the user and the application are both binary, either 0 or 1. And finally, the conclusions. The application ecosystem is formulated by a quantum game model, which has entangled inputs, taking advantage of two entanglement degrees to depict the power of the light slide and the dark slide. And the second one is the relationship between the optimal strategies of players and their entanglement is deduced, through which we can quantitatively obtain how the reputation influential power of the application and the adversary impact the development of the application ecosystem. And the third conclusion is that two special cases are also analyzed. As supplements, such analyses make the study for privacy leakage in the application ecosystem complete. That's all.